Video lesson 12.1. So today we're going to utilize coordinate geometry to help us determine area and perimeter of figures. So let's look at this first one. Let's plot these points. We've got O is 0, 0. That would be there. This is O. We've got A is 5, 6. So 1, 2, 3, 4, 5. 5, 1, 2, 3, 4, 5, 6. And lastly, B is 4, 1, 1, 2, 3, 4, 1. All right, so here's our 3 points. As we can see, this makes a triangle. So if I was asked to find the area of this, right, you can start with the area formula, right, which we know is A is equal to 1/2 base times height. But here, I'm looking at these sides, and I don't have any indication that any of these sides are perpendicular to each other. And I could obviously calculate them. I could find the slope of each line and look to see if I in fact have opposite reciprocal slopes, which would tell me that they're perpendicular, which would then allow me to know that one of them's a base and one of them's a height. And I could calculate the lengths and plug it in. But I can tell you right now, these are not perpendicular and none of the sides are. So how am I going to do that otherwise? So I got to figure out a way to do it without using the formula. So without having to use the actual area formula, I could take this and kind of go back to our old thought process here. And that is make a giant box that encompasses the entire figure. So I could make a box here. All right, like so. All right, and basically break this up into figures that I could find. So here's one right triangle. All right, here's another one. Here's another one. And then that gives me just this little box here. So what I could do is I could find the area of all of these little pieces, right? And say, well, the area of the entire thing, if I remove each of these, right, that would be the area of the triangle. So think of area of shaded region, right? So in this case, the area of in this case, the blue triangle is going to equal, let's call this the big area of the square, right? Actually, no, I'm sorry, not a square, it's a rectangle. So we can do the area of the rectangle minus the area of, let's call this 1, this 2, this 3, and we'll call this one over here 4. So we got area of triangle 1 plus the area of triangle 2, plus the area of triangle 3, plus the area of that little square, which is 1. So I can do that for each one of those things, right? All right, so let's go through that process. So area of the rectangle, this is 6, this is 5. So the area of the rectangle is just going to be length times width. So that's 5 times 6, so that's 30. That one wasn't bad. We can find the area of each piece. So the area of the first triangle, that's going to be 1/2 base times height. Let's call one's a base, one's a height. So that's going to be 1/2 5 times 6. So that's half of 30, which is 15. So again, we're subtracting here 15 plus area of this second one here. So area of the second triangle, that's going to be 1/2 of, let's call this the height, this the base. So base is 1, 1, 2, 3, 4, 5. So that's 2.5. And the area of the third triangle, that's down here. We've got a height of 1 and a base of 1, 2, 3, 4. So 1/2 4 times 1, which is 2. And lastly, the area of the square, which is just a 1 by 1 box. So 1 squared is 1. So if I add those all up, right, from here, that gets me an answer of 30 minus this total here. So 15, what is that, 20.5, which is going to get me a final answer of, what is that, 20.5 minus, so it's 30 minus, that's 9.5 units squared. That would be the area of my blue triangle. Now, that's fine. Everything we did there, nothing super complex other than the fact that you have a lot of area formulas that you got to figure out. And that can get time consuming, right? But it's doable, right? And kind of a last resort is just dealing with it in that format. But you can kind of see how they could have difficulty, especially if these become a little bit more complex figures and a lot more images will have to be done. But that's the concept. So we do have the fact that we're dealing with coordinate geometry and we have actual points and the ordered pairs. We could actually use another method, and that's called the shoelace method. So here we've got the shoelace method. All right. So first off, we got a first step here is pick a point. Doesn't matter which one. Pick one of these points. O, A, or B. Doesn't matter. I'm going to pick A. So I'm going to start with A. That's 5, 6. Okay. List all the points in order, clockwise or counterclockwise. Just be sure to start and end with the same point. So I'm going to start here. So I'm going to start with A. I'm going to go around the figure. I'm going to go clockwise. So A to B, right, it would be 4, 1. Then from B to O would be next, 0, 0. And then lastly back to A. Because you want to make sure you go around the figure completely. So again, what did I just do? I went from A to B to O back to A. So I've gone around the figure, so to speak. There's all my points in line. Again, notice I've started and ended with the same point, okay? That's key. Now, next step says diagonally multiply each point of numbers in both directions. So what I'm going to do here is I'm going to take a diagonal line from each one of these. So 5 times 1, get a value. 4 times 0, get a value. 0 times 6, get a value. I'm going to do the same thing in the other direction. I'm going to go this way. So 6 times 4 is 24. That was, oops, I lost my point there. 4, 1. So 1 times 0 is 0. And 0 times 5 is 0. Obviously, with the zeros, this makes this a little bit easier, but the process is the same. So I've done that for both of them. All right, and hence the shoelace method. You can kind of see how this looks like the crisscrosses of a shoelace. So now each of those columns that we just did, we're going to total them up. So I'm going to add these up here. I get 24. I'm going to add these up over here. I'm going to get 5. All right. So that's how I got each of those values as my next step is indicated. Add up each of the columns. And this next part, and this is where you got to remember, this is why the order doesn't matter as long as you follow this step here. You're going to take the larger number and subtract it from the smaller number, then divide by 2. So the area is going to equal the larger number minus the smaller number divided by 2. So I can now say the larger number is 24 minus the smaller number, which is 5, and divide by 2. So if I take that there, right, I've got 24 minus 5, so what is that, 19. Divide that by 2, and that gives me 9.5 units squared. That is the same value we got up here, up there. So you can see this is a nice little shortcut, right? That allows us, that's sloppy, let me fix that. Nice little shortcut in allowing us to find the area of any polygon. That's the beauty of this. It does not have to be a rectangle, it doesn't have to be a triangle, anything like that. It can be any polygon. As long as it's a polygon that's closed figure, you can do this, and you have to have the points, obviously. But this is a nice little shortcut. You do have to remember the steps and the process, but it is a nice little shortcut. This process will be much, much faster in the grand scheme of things, especially the more complex the figures themselves get, okay, from there. And that's called the shoelace method, all right? So let's take an opportunity to try that again using another one. So I'm going to come over here. Let's plot these points. Just for argument's sake, I'm going to label all of these points with names just so it's easy to describe. So we've got 3, 4. I've got 5, 11. Oop, we're running out of space here. You know what? I'm going to redraw this grid lines here because this is not going to fit on this graph paper. So that's going to cause me a problem. But actually, you know what? I don't even have to do that because there's no reason. I'm not going to do it with that. So, but here's an example where I'm not really on that graph paper. I'd have a difficulty. I'd have to redraw the whole thing. So it's actually a good example to show like where we can just use this and find the area without even having to graph it. So pick one of the points. Doesn't matter which one. We'll start with A. So 3, 4, and then 5, 11, then 12, 8, 9, 5. Oh, you know what? As I do this, I'm realizing one thing. I do have to make sure though that these are that I'm going around the figure properly. Just because the order here does not necessarily means the order is actually there. So you know, let me actually try to plot these just real quick. I'll sketch them. So let's redraw this here, like so. So that'll be my new X and Y. So 1, 2, 3, 1, 2, 3, 4, 5, 11. C is going to be 12, 8. We've got 9, 5, and then 5, 6. So this was A, B, C, D, E. So it was actually in order, which is good to know. But I had to confirm that. I can't just assume that the ordered letters goes in the right order. But all right, so let's go back. So again, I chose A, so let's go back to that. So 3, 5, 11, 12, 8, 9, 5, 5, 6. Again, I started at A. I have to finish at A, so I need 3, 4 to come back. If I don't put that one, I haven't gotten back to it from there. All right, so now let's do our little cross multiplication part. So 3 times 11, 33. 5 times 8 is 40. 12 times 5 is 60. 54. 20. All right, let's do the other way. I've got 20. 121. 72. 25. 18. From there, all right. Oh, actually I have one calculation error. 11 times 12, that's 132, not, sorry, I read that wrong. All right, so let's total these up. Let's get a, for each of these columns, so let's get a total here. So let's add those all up. We've got 20, 132, 72, 25, and 18. Gives me a grand total of 267. And we've got 33, 40, 60, 54, and 20. That's going to give me a grand total of 207. So now, again, to find the area is going to equal larger number minus the smaller number divided by 2 using this little shoelace method. So 267 minus 207, divide that by 2. And that's going to be, what is that, 60 over 2. So that means it's 30 units squared for the area. All right. And again, I could have made the big box, but as you can see, if I made the big box here, I would have had a lot more figures to do. Because just real quick, just to kind of sketch it here. So here's my big box that goes around everybody, right? Then I would have had to make another one here, and then another one here, and another one here. Like, that's a lot going on there. I mean, it's doable, completely doable, but a lot more involved than I really want to. And honestly, this one would be a little bit more, so I probably even have to make an extra one, something like this. And again, you're just getting way more involved than you need. I can use this much, much faster by just simply using this shoelace method. All right. So We're getting a little lengthy here on this video, so I'm going to allow you guys the opportunity to kind of try these other ones on your own. But as hopefully you got the understanding and the concept of what to do with the shoelace method. Again, make sure that you have the steps down, copied down, and allow yourself a chance to try these from there. All right. And again, when you're trying to find perimeter, you have to use the distance formula. So I would just simply actually be finding the distance of each of these lengths if I was looking for the perimeter, and then you just simply add them all up. So it is a little lengthier of a process a lot of times when asked for perimeter, but it is something that you could be asked to do. So, all right. So take the opportunity to review these questions and take some notes, and then utilize the practice problems for more understanding.